Welcome to Software Gone Wild, a podcast focused primarily on SDN as well as everything else software-defined. I'm Ivan Pepelniak. You'll find me at ipspace.net, where I blog and occasionally do webinars. And today we'll have a routing protocol-focused show, and I have two co-hosts. Let's start with the star co-host, Ethan Banks from the Packet Pushers fame. Ethan, how are you doing?
Doing pretty well. Thanks for having me on, and I'm looking forward to...
Thanks for coming on this show.
Yeah, this will be enjoyable because it delves into a routing protocol that does things I didn't really think you could do. So this will be interesting.
Absolutely. And my other co-host is a regular, David G. How are you doing?
I'm really well, thank you. How is yourself? Are you well?
I'm doing well. I'm starting my autumn road trip tomorrow. And after that, it will be, I don't know how many weeks of SDN workshops all over the world.
Hey. How about that?
Yeah, so vacations were fun, and now it has started.
Indeed. Well, thank you for having me. Looking forward to this, and I've read very little of anything about this, so this is all exciting stuff.
And let's make it even more exciting. With us is Marcelo Spon. And Marcelo, would you introduce yourself to the audience? Tell us what you're doing, how you became involved in the routing protocols.
Yes, Ivan and Ethan, David, first of all, thank you for having me, Raghu, here today. You know, your level of expertise on this podcast is incredible. It's fun to be here, and I'm sure we're going to have an incredible time today. Well, you know, I'm a founding member of Adara Networks, and I'm currently the chief scientist. We develop SDN solutions. We have production-ready SDN platforms, and I'm responsible for developing the advanced networking platforms at Adara. I have worked in my entire career in networking. It all started at university, and especially when I did my graduate studies back at UCSC under the supervision of J.J. Garcia Luna Celes. Back in my graduate studies, I did research in wireless and mobile networking, especially in routing protocols, unicast and multicast routing protocols. And afterwards, I started working for a company called Rooftop Communications that was acquired later by Nokia. And Nokia started a division that was called Nokia Wireless Routers. And there I was the lead network protocol engineer. At Nokia, I continued to work on developing a wireless IP router that we started at Rooftop. And then came Adara.
Perfect. Thank you. Another guest we have on the show is Raghu Gangi. Did I get this right?
Yes, Ivan, you are right.
So what are you doing?
First of all, thank you very much for providing this opportunity to be on your podcast. I listen to your podcasts and read your blog posts and find them very informational. And even Ethan, I read your blogs too, and I find them very useful. I'm in Dublin, California, and it's pretty early in the morning. So coming back to my introduction, I work as a principal engineer at Adara. I lead the team for the switching platform. I'm also involved in collaborations with open standard communities like ON Labs and ONS. So we participate in some applications over SDN. And we try to use DLSP in various applications and try to extract more out of SDN. We basically provide production-ready and vendor-neutral solutions from Adara. It has various use cases like we do WAN, we do virtual CPEs, we do virtual network functions. My work mainly involves working on SDN and cloud OpenFlow switches built on Trident 2 platform. We use OpenFlow data plane abstraction SDK from Broadcom. And I take the complete ownership of the production code from the development team at Adara.
Okay, so I have to ask the question. Are you working with white box switches or do you ship your own switches?
So we actually have both. Our software doesn't have anything specific to Adara, but we are a ODM. So we have our contract manufacturer who manufacture white boxes for us. But that doesn't mean we don't work on other white box switches. We are based on ONI and the normal Linux with Broadcom SDK. So we work on everything, every white box switch based on Trident 2.
So effectively, your company is making software. And if someone wants to buy a hardware product from you, you just take it from ODM, put your software on it, and ship it as Adara branded switch to the customer.
Exactly, that's right. And we also work on Tomahawk as well. So those are the two leading ASICs in the industry as of now.
And you are using, if I understood correctly, the OpenFlow to program the actual switching hardware?
Exactly, yes.
And then I'm guessing that whatever is on the north side of this OpenFlow, the controller is then using DLSP as the routing protocol with other instances around the network.
Yes, like we call it path computation engine, but internally it's powered by DLSP with all its QoS awareness.
Mm-hmm.
So when you call it path computation engine, do you mean what the industry means by PCE then, or are you just using the same terminology and it's actually, because it's something different on the back end?
It's very different in the back end. So it's more to put in line with the industry terminology, but we have specific features which are more dynamic and which kind of segregate different layers in the networking architecture these days, like the optical layer, the packet layer, and the applications on top of it. So our PCE, like the DLSP, is very programmable. It can see the different layers and compute the path effectively and push the flows accordingly into the hardware using the controller.
Okay, so is the controller running on each switch and then running DLSP between the switches, or is the controller a centralized thingy somewhere that is controlling a group of switches and run DLSP with itself?
Oh, that's a very interesting question. So we have both the architectures. We have some customers who request that they can't have the latency of the switch communicating to the controller over the network, which actually increases the latency in all the packet in, packet outs, and the like event notifications, etc. So our controller is actually highly scalable, distributed, and it's cluster based. So we have an instance where we run controller on every switch. We also have a distributed cluster of controllers which manage somewhere between 100 to 200 switches. But the controller can scale up to, we tested up to 5,000 switches. It works perfectly fine. So both modes are supported based on the customer needs.
And you mentioned DLSP a number of times. Where would DLSP fit into this picture?
That's a nice question. Before going into DLSP, I think it's better to understand what basically the DLSP does. Marcelo, can you please go ahead and explain?
Yes. DLSP, it's going to compute multiple paths, and the paths, they may be of unequal cost. So DLSP makes, besides computing multiple paths of unequal cost, DLSP also is going to probe periodically the performance of the links with its peers. So that means that it's going to find out dynamically in real time what is the bandwidth of your router, what is the latency, what is the available bandwidth, if we're talking about an overlay network, and what is the error rate. So the link metrics are computed dynamically, and the routing protocol disseminates this information in a different way that's not based on topology flooding to its peers, and computes the multiple paths, the multiple shortest path trees, you can say. And with this information, then the switches are able to apply the QoS policies that you specify for the applications.
So are those, is this all distributed where each individual node is running a DLSP instance and from its own point of view, running these probes, determining link performance, determining available bandwidth, etc.? Or is it, handled from a central controller that instructs the DLSP nodes to perform these actions, or?
Yeah, Ethan, that's an excellent question. DLSP is a completely distributed routing algorithm. It doesn't rely on the controller for anything. Essentially, so it's a completely distributed routing protocol, and when you deploy when you configure the router, essentially the only thing that you need to say for DLSP is, hey, you should work on this set of interfaces or this set of tunnels. That's it. It's self-tuning, self-adjustable to everything. And as I said, it does not rely on any central point of management configuration. It runs like any other routing protocol, like OSPF, right? It's a completely distributed routing algorithm.
So to tie this back with your SDN architecture, if your SDN controller is using OpenFlow with controlled switches, then those switches are obviously pretty dumb. So does that mean that you are running DLSP between individual controller instances and establishing sort of a federation of controllers with DLSP?
Ivan, that's a very nice question. So actually, let me explain you a little bit more in detail. Like we have scenarios where the switches use some legacy platforms like VxWorks with not such much horsepower. In that case, the DLSP can run as an application on top of controller, and it identifies each switch based on the DPID, and it can use OpenFlow's packet in, packet out messages to send the probes or the hello packets or the LSAs to exchange the routing information. And also it can use the OpenFlow metering to do the rate limiting and QoS controls. As well as it can get the statistics using the OpenFlow statistics messages. So it basically depends on what kind of equipment we are running on. If it is a Linux-based white box where the DLSP can run directly on the switch itself, then it's good and it's by far the best way to run it. But it doesn't eliminate us from running it on controller. But yeah, there are some latencies that are involved when DLSP packets are sent back and forth through the controller to the switch. We have some adjustments in latency calculation that we can do based on the probes that we do between the controller and the switch for it to program the flows and send the packets out. So does that answer your question?
Mm-hmm. So the ideal use case is that you have DLSP running on each individual physical box. Mm-hmm. But if you can't do that, then you can run it through the controller and you adjust for the latency between the controller and the switch.
Exactly. So in fact, what we do is DLSP can talk to the traditional legacy protocols. It can redistribute the routes from OSPF, BGP, and it can switch between SDN island and the legacy island. So it's like you can run it on controller and speak to the legacy networking protocols.
And also, we have several different form factors. We also have a DLSP running in x86 platforms, in bare metal, or as a virtual appliance. So we have this embodiment of the routing engine that does not need to rely on an OpenFlow controller. So on this form factor, DLSP it can run as I said, as a virtual appliance, and where you can provide QoS routing on the WAN, so without needing an OpenFlow controller.
So this is a good segue here into the QoS routing element of this. Now, if we talk about software-defined WAN, what that means to those vendors when they wouldn't use the term QoS routing, they would say application-specific routing, is they'll identify an application by some means, they vary by platform, and then make a forwarding decision based on some policy that's been sent to them by the controller. This link looks good for this sort of a flow, I will forward across this link. Now, when you say QoS routing, I mean, the SD-WAN guys can get very granular with the kinds of applications that they wish to forward in some particular way. But in a distributed routing protocol like this, when you say QoS routing, how many classes of traffic can you make unique forwarding decisions for, and then how are you identifying that traffic?
Mm-hmm. Yes. Well, we support QoS based on several constraints, such as, you can specify a policy requirement for an application based on the latency of a path, or based on the bandwidth of a path, or a combination of both latency and bandwidth. You can say, hey, for this application here, I want you to map sessions of this application to a path whose bandwidth is at least 10 megabits per second and whose latency is at most 50 milliseconds, for instance. So whenever a new session arrives, the forwarding engine is going to map a session to a path whose performance is closest to what you specify in the policy. And you can also specify emission control policies for the session. You can say, hey, for this class of application here, I want you to reserve at least 2 megabits per second. But another very critical thing here is that you don't need to worry about doing traffic engineering here. The user just needs to specify what are the bandwidth requirements, the latency requirements of the application, and DLSP and the multipath forwarding engine is going to take care of mapping the session to the right path. And the core of this is of being able to provide this kind of QoS awareness is that the routing protocol, DLSP, probes constantly in real time the performance of the paths. And then this allows us to work, for instance, to use simultaneously multiple circuits with different properties, with different transport protocols. For instance, you can have a branch connected to a data center using a lease line or an MPLS link, as well as broadband links all together. So with DLSP, we're able to use all these links, all the paths over these links simultaneously. And because of the way that we compute the performance of the paths, we can make utilization of the broadband links in pretty much the same way that we do for lease lines. So if a broadband link now, we see that they're perceiving that we can route voice over it because the latency is good. They're going to route voice over it. And these are several implications, especially in terms of saving money, so reducing costs.
Okay, but coming back to Ethan's question, now you said you can specify voice has these requirements or SAP has these requirements. But somehow the switches have to identify what voice is or what SAP is. So are you using diffserv code points to do that, or are you using flow specs?
Yes, Ivan. You can specify the application in several ways, what we call policy selector. You can use a diffserv code point to identify the application, or you can use a combination of port numbers, IP addresses, subnet addresses. You can say all the traffic that comes, for instance, from this subnet here, should be mapped to a path with these properties, with this performance. You can also specify a DPI rules. So you can say, we have a DPI engine. So you can say, hey, all the Skype traffic should be mapped to such a path with such properties. So the policy selector is, you can have a combination of these. You can have a combination of port numbers and IP addresses or subnet addresses, diffserv code point, and as well as a DPI rule.
Now, when you say we have a DPI engine, do you mean in the Adara ecosystem, you could use a DPI engine that doesn't necessarily have anything to do with DLSP, but use that data to inform DLSP? Or are you saying that there's a DPI engine built into DLSP itself?
Oh, no. It's a separate product.
Yeah, it's kind of a service chain that you can do. So the DPI can feed into the DLSP.
Okay, so am I right in understanding that from the user perspective, you can say, this is how I identify the application. This is the requirements for this application. And then DLSP takes over and dynamically propagates the requirements throughout the network. And then every node in the network would find a path or a set of paths that meet those requirements and can be used for traffic forwarding.
The policies, the QoS policies, as well as which is essentially they are all pushed to all the devices that are on the network. So all the devices they know how to identify a particular application.
So is someone then a master in the system? In theory, you could do a policy on multiple devices and have conflicts and so on.
Mm-hmm. Yes. There is what we call a network designer, which is a tool so that every router connects to pull the configuration, the policies. So we use this tool to configure the global policies, and then when you change the configuration, this tool is going to push the change to all the devices.
Yeah, and apart from that, we have a concept of a global policy as well as a local policy. So a few policies can be applied to all the routers in the network, and few can be applied only at the edge or at the entry points. So it all depends on what the use case is. Like we use both the configurations.
But the distribution of policies is done sort of on the management plane, right?
Yes.
So it's not part of the DLSP routing protocol.
That's correct.
So I'm guessing that within the routing protocol, you're just saying I have these X traffic classes, and well, traffic classes are whatever is defined somewhere else. And these traffic classes have these requirements, and now let's find paths that meet these requirements.
Exactly.
Okay, so how? What I'm trying to get my head around is how quickly a network landscape can change. Do you ever come across any conditions where you have like a relay race where packets make it across a network, the conditions change, and then you inadvertently form a loop? So how does all that work?
Oh, okay.
I mean, is there end-to-end signaling as well? I mean, I can't quite get my head around some of this yet.
That's a very good question. Yes. Then we are talking about the overlay networks, where the other routers are connected with tunnels, IPsec tunnels. What happens here is the following: the DLSP is tightly integrated with the multipath forwarding engine. You can think that we have like in-band signaling on these tunnels, or between the edges of the network. The routers connect to the edges, meaning that we have some. What happens is you can think that we have like virtual signals between the data routers. Okay, we have some signaling that mimics that, meaning that when every data router is going to the multipath forwarding engine is going to keep track of the utilization of the links of the tunnels. And if utilization of a link with a peer starts to exceed a congestion threshold, then this information, this utilization of the link is propagated to all the routers that are using that link. They have sessions mapped to that link. So all the routers get to know what, that the congestion threshold has been exceeded. What happens then is every router that is using a session mapped to that link, they are going to try to reroute the sessions to least congested links. So that's essentially how it works. We have in-band signaling on these IPsec tunnels, and the forwarding engine also has it's not just the DLSP runs at the application layer. The forwarding engine in the kernel is going to have some also in-band signaling with its peers to get to know what's going on the tunnel with its peers.
Okay, and then I imagine then you can move some of a load from an interface to another path. So you could say maybe move a couple of flows from one path to another. I mean, you don't want to be in a position, do you, where like TCP synchronization, where all of a sudden all traffic of a certain kind goes down one interface, and then because it's hit a threshold, all of it's moved to another interface?
Oh yes, no, that's correct. We are very conservative in that regard. So the goal is to stick a session to a path and leave it there as much as possible. And if we do need to do the rerouting because of congestion, for instance, then you move to a path that we are sure that we can hold that session, try for that session. And we can do that because we know in real time, first of all, what's the bandwidth of the path? And what is the estimated available bandwidth? So we have a way of identifying essentially on an overlay network what kind of a notion of what is the cross traffic going on the underlay network. And that's why we can remap the sessions to another path, without disturbing for instance, TCP.
Interesting.
So we kind of maintain session stickiness, and only at the last resort we try to reroute it, an existing session. We try to usually use a new session to route on a less loaded path, unless the existing link becomes so overutilized that we need to reroute a new session.
Yeah, like you said, it makes perfect sense, doesn't it, being more conservative? So I guess in summary then, and just shoot me if I'm a bad person for saying this, it's like a more dynamic RSVP-TE, isn't it?
Yes, you could think in that way, and without the need for configuring it, right?
Sure,
so,
yeah, I like that.
That's the major contribution of this routing solution, simplify the deployment on WAN links with similar costs, and then provide QoS without needing to do traffic engineering.
Yeah, if you think of it in a way, it's kind of combination of policy-based routing with RSVP traffic engineering and the very efficient routing protocol, which uses partial link state. So if you see the numbers of the convergence and the chattiness of DLSP, it is way more efficient than any existing protocols. For example, if you take it actually is almost 50% faster than the distance vector protocols, and it's very, very less chatty. It almost takes 23% fewer updates than in LSAs, and 80% less than the link vector algorithm. So it's very, very efficient. It doesn't flood the full topology state into every node. It is basically a partial link state based thing.
Okay, before we go into those interesting topics, let me just try to recap what I understood so far and what you just mentioned. At every node, you have the definition of what the policies are. And as you said, you're using that for PBR in double quotes. And then you have multiple unequal cost paths to which you could map a certain class of traffic for a certain destination. And there your routing protocol generates something that looks like multiple tunnels going to the same destination, if we are speaking now in MPLS-TE terms. And you're shifting the ratios of how traffic shift between these tunnels based on the actual state of the links.
Exactly. Yes, that's very, very right.
By the way, now that I mentioned MPLS-TE, do you need any special encapsulation between your devices, or is it just plain IP and you just use the same PBR rules on every box to get the packet to the right destination?
Yeah, it's just a plain IP. The encapsulation is based on vanilla IPsec.
So, and also like one more interesting thing is we can use any LSPs that are set up by an MPLS provider. Actually, we came across an interesting use case where the DLSP can take advantage of something like an optical express path, which can be established by optical circuit switches. So that's very interesting. Like within your network, if you have a segment which can be established by programming simple flows into the optical circuit switches, the DLSP can take advantage of them and establish that path. So it effectively is kind of DLSP has a capability of segmenting the network into multiple segments and fit the best possible, in open flow terms, flows into the corresponding switches based on its capabilities, and then use them and route or switch the packets.
Did you just say that you're interacting with GMPLS and set up optical paths on demand if that's available?
That's right.
That's cool.
So we are working with one of the vendor who has a very innovative way of doing optical circuit switching at the light. So their uniqueness is that we don't need to convert the optical packet into an electrical thing where you introduce a latency. So if you have a scenario where you need to do high traffic intensive activity, you can actually set up an optical express path using DLSP working as a PCE, and then the data can be forwarded and the path can be disassembled after the transfer is done.
But it's still optical switching, so it's lambda in, lambda out, right?
Exactly. Yeah. It's kind of a reflection. It's like a mirror where you switch the optical.
You can't touch the packet in transit, right?
No, we can't modify it. It's just switching, yes.
Now I'm waiting for the optical gear to be able to actually switch packets, but I don't think it will happen anytime soon.
So
yeah, that would be interesting.
I have more questions around the actual implementation of DLSLP. In terms of itself as a protocol, then, how is it actually implemented and how does it appear on the wire?
DLSP? DLSP is implemented on top of UDP and TCP. So
okay.
DLSP it sends the probes like DLSP periodically send hello packets like in packet trains with peers to measure the bandwidth, to estimate the bandwidth and available bandwidth. So the probes are these hello packets. These trains are sent on UDP, and some of them are sent in clear text. Some are sent on IPsec encrypted, and DLSP also to exchange the link state updates with these peers. It does that through a TCP connection.
Okay, that makes sense.
Yeah.
Okay, interesting. You just touched on something there as well, which is quite interesting. So the way that DLSLP will figure out the capabilities of an interface and different classes, is this something along the lines of it will kind of generate synthetic traffic? And it's slightly different than the competition, isn't it? Or let's say the standard way we think about it, where the size and say the streams of the traffic can be generated differently to try and figure out the kind of, I guess, the characteristics of a circuit.
Right. Oh. Yes. What happens is the DLSP it sends these packet trains with different sizes, different number of packets. The size of each packet on belonging to the train also changes. So, for instance, if it identifies in a very few couple of runs, if it identifies that for instance a T1 circuit, it's going to send the probes in a very low rate compared to if you had a 100 megabit link, for instance. So it self adjusts to the characteristics of the medium. So yes, the packet trains, but there are several approaches on the academia or commercial available for estimating the bandwidth, right? But the novelty here on the DLSP side is that this probing is not intrusive. We send these trains, they are small, and we send them periodically by default every 10 seconds. But the overhead, the communication overhead is negligible. So the novelty is in how to make use of these trains, and there are several heuristics, and then to estimate what is the capacity of the link, and then also what is the available bandwidth.
Yeah, and just to reinforce that, we actually did implementation for a satellite communication based on TDMA, And Marcelo actually has done the changes of spreading these trains across different time slots because the SATCOM has a different way of working. And so it kind of, you need to send packets across different time slots in order to reserve those time slots for your equipment. So I can say that DLSP is very customizable based on different needs of the network. Like you have different needs for an optical network, you have different needs for satellite communication or the normal packet network. And one more important thing, like from the earlier question, DLSP uses TLV based packet exchanges. So you can actually, in principle, you can exchange any information that you want. It's just like ISIS in that perspective.
So, which brings me to the question of address families and the obvious question, does it work for IPv6?
Beat me to it.
Yeah. Yeah. The current implementation, no, that it works on IPv4 only. That's on the roadmap, though.
But if it's TLV based, it's just adding another address family, right?
Yes, but there is more work involved in that regard. But essentially, it doesn't require that much effort. But yes, it's
well, it's one thing to carry IPv6 as an address family, but it would be another to do probes and so on and have the control plane run over IPv6. So which elements of that are on the roadmap?
Well, on the roadmap, it's supporting a dual stack. So it's really supporting, two stacks simultaneously.
And then you will, as Ethan mentioned, do probes over IPv4 and IPv6 in parallel and independently?
Oh, yes. Now, the idea is that is to replicate all the functionality in IPv6. So we are going to have the same functionality. The control plane is going to work the same way as we do in IPv4.
Yeah, that's an interesting question. It could be possible that the latency measurement that we can do in one can be used for the other because it's the link utilization. So that's a very interesting question.
Yeah. If you are working on physical links and you have your nodes on both ends, then I totally agree with you. You should reuse the latency results. But if you're working over tunnels, there are cases where one of these protocols is faster than the other.
Then you're going to have a tunnel, for instance, that is running on IPv6, another tunnel running on IPv4. Each one of them you're going to have to do the probing on each one of them. And as a matter of fact, you can even have two tunnels running across the same physical path. The way the algorithm works is that it's going to treat the second tunnel as like cross traffic, and there is some self-adjusting mechanism there to deal with that. So that should not be a problem.
But just thinking about this, you could do a variant of happy eyeballs and just send the traffic over whichever tunnel is faster.
Yeah.
By the way, previously you mentioned something called partial SPF.
That's correct.
What's that?
Yes, that's even is the following. For this OSPF, it relies on topology flooding, right? Every node inside of an area is going to know the state of all the links in that area. First, DLSP, it assumes a flat network model. You can have a hierarchical routing if you want, but the assumption is a flat network. And what happens is DLSP is going to report to its peers only the state of the links that are part of one of the shortest path trees computed. So if a link is not in one of the shortest path trees computed, that link is not going to be reported to its peers. So that's why the nodes, they have partial link state information. So if the cost of a link changes, so if you are the head of the link, of course you're going to report to your peers the change of cost of the link. But the peers, they are only going to relay the state of that link to other peers only if the node itself uses the link in one of its trees. Otherwise, the state of that link is not propagated.
Yeah, and that makes it very less chatty, and that also makes you free of configuring different areas, and because OSPF is basically divided into multiple areas in order to reduce the chattiness. Since you distribute your link state database across all the nodes in an area, so it is a huge set of information, and in a bigger network that becomes too much of LSP packets that are going through your network. So since this novel way of just identifying the affected nodes and propagating that information only to them actually makes DLSP converge much faster than any other routing protocol.
This sounds almost like a mix between distance vector and link state routing.
Yeah, that's correct. Yes. That's the end result.
Did one of you not work with somebody who worked on the IGRP? Sorry, so let that one slip.
Actually, Marcelo, JJ designed EIGRP, right?
Yeah. Well, JJ was my advisor back at UCSC. He developed the algorithm that is the core of EIGRP, which is called DUO, diffusing update algorithm. That algorithm, EIGRP, is the one that it determines whether a routing update should be generated for a given prefix, and it essentially it prevents the routing loops from forming in EIGRP. Yeah, so I work with JJ, and JJ essentially was my mentor here.
But the big difference, if I understand what you're doing, is that in EIGRP or any distance vector protocol, every router is propagating the cooked information. So what it is using from its forwarding table, whereas what you're doing is you're providing selective raw information.
That's correct, yes. And the routers only report the state of the links, nothing else. So it's up to each node to run this distributed routing algorithm to decide, whether or not that link is going to be part of one of the shortest path trees. And now also another important thing to consider is the following. Somebody could say, hey, EIGRP also can do multipath routing over paths of the similar cost. And the answer is yes, but in a very limited way. And even on very small topologies, EIGRP can only use a subset of the paths, of the available paths, because of the way of this loop prevention algorithm works. And DLSP on the other way can make use of all the possible paths. Another thing is that EIGRP, all the link metrics, they're statically configured. So if you want, for instance, to do traffic engineering, you will have to go there and configure the metrics of each link in order to make it, that path, the preferred path for a given class of traffic. In DLSP, no. DLSP, all the link metrics are computed dynamically. The user doesn't need to never ever, configure anything in that regard.
Interesting. So I guess then the ability to use all of those paths is that absolutely reliant on OFDPA to achieve that?
No, not really. I'm sorry, Raghu.
No, go ahead, Marcelo.
Yeah, there are two frameworks. One is where we work on let's say on the x86 platform, and the other one where we work on the switch side.
So we can't obviously do everything that we can do on an x86 on an ASIC, but we try to mimic most of the features. Like our x86 forwarding module, which is actually very different from any traditional forwarding element. It does a lot of session-based, like you said, the session stickiness, everything can be done there. So it's much more effective.
Oh yeah, this is a very important point. Is that the forwarding engine on the x86 platform is completely session-based, meaning that with the head switch now that is connected to the source of a new session, for instance, it maps the session to a given path. And there is an inline band signaling, making sure that that session is indeed mapped to all the intermediate routers until it gets to the tail AR, a data router. So, it's session-based routing. It is not, packet-based routing. That allows to, that's one the key for doing QoS routing for instance, on one side on an overlay network.
Okay, I mean, the x86 module as well, and in terms of performance of the actual data path forwarding, is that kind of DPDK ready?
So we are currently working on moving it to DPDK. Currently, it is a kernel module. It runs within the kernel space, and the DLSP running in user space actually programs the rules into the kernel.
Okay.
So we
DPDK,
are
I
actually
assume
working
that's-
on the DPDK. Yes.
It's going to drive much bigger performance, I'm assuming then.
Yes. So it actually depends on the actually where we are trying to put it. If you are putting on the WAN side, you probably don't need like a 10 gig throughput or so, because most of the customers we work with, they actually have less than 200 Mbps, which we can actually meet with the current forwarding plan. It can actually scale up to 1 Gbps. But yes, we are working on DPDK to enhance it to be at near line rate.
Mm-hmm. Is there a standards track for DLSP, or is Adara going to keep this in-house?
We have a plan to make it a standard because it becomes useful. Like once it is a standard, we can interop with any of the vendors and all, because the uniqueness is within the implementation. It's not the specification of the packets or the logic or the any such thing. So I think the Adara's IPR is going to be the how we probe the latency and how do we do the implementation of it. So we are working on making it a standard, but I don't know how long it's going to take.
So
but
you're
we
saying
are pretty
that
much interested in it.
Okay, you could do it as a standard, and then again, what would be a differentiator from vendor to vendor who chose to implement that standard would be in the details. The standard wouldn't be written so granularly and in so much detail that the way the probes are executed would be defined in the standard. Rather, the general framework of DLSP would be defined, and then you as a vendor can choose to have some latitude in how you actually execute on some of those things.
Exactly. So the RFCs are mainly for interoperability, so that you understand the packets I send, but how you send the packets and how you measure the link, they usually are kept outside the scope of the RFCs.
But again, there's no current IETF draft for DLSP. It's just something that Adara is considering, and probably you're going there. But do you have a timeline, or?
Marcelo, were you working on it?
Yeah, no. Right now, yes, this is something that just started. So we don't have a timeline yet. But the goal is to make the path computation engine part of DLSP a standard. So the logic for computing these multiple paths of an equal cost and how to use them. No, we don't have right now a timeline for that.
So since you asked this question, so I just want to tell you about some implementations that we are doing with some of the open source communities. Like we are working on developing a PCE framework within ONOS, Open Networking Operating System. We are collaborating with ONOS for various use cases like data center to data center interconnectivity, and also central office re-architected as a data center, where you have hundreds of thousands of central offices and you need to interconnect them using packet optical switches. And DLSP is a perfect fit here because it can understand the packet layer dynamics, and optical layer is more kind of a stable thing, but there is no configuration that current implementations can do. They're more of a closed systems. So we are working with them so that we can provide a framework for a PCE and any other PC in the market can use that interface to do that. So we are collaborating with them so that it becomes a kind of a standard way of implementation.
Does that mean that there is a DLSP daemon in the wild that's open source that anyone could run, and you're using that in coordination with ONOS?
That's an interesting question. So what we are trying to come up is with a framework, what all hooks the PC needs in a controller to program the switches, and what are the high-level intents that can be there. But the actual implementation, we haven't thought whether we want to put it in open source or not.
You're at a higher level. You're saying we want to provide a generic PCE framework. The way we'll implement it happens to be with DLSP, but we're just really giving you a way to do path computation generically.
And also like various hooks, like dynamically inputting the latencies and the link utilization.
Yeah, would this not suggest that you'd also need to distribute agents around to generate probes or report back to a kind of centralized PCE? I was just trying to go through this in my head. It's a really interesting use case. So, and also it suggests some tracking as well. So you might have a lot of state kind of stored in one place, or obviously maybe in a cluster or something.
That's one more thing. Like it's kind of DLSP can scale very well, and we can actually synchronize the state across multiple instances. So we could have two DLSP, so like if controller is running in a cluster mode, then we can have the redundancy, so it's not a single point of failure. But yes, so does that answer your question?
Yeah, thank you for that. This is really interesting stuff. I think we could do another show on this as well. It's quite a nice big area, isn't it, really?
Oh yeah, we definitely have to do a deep dive.
Yeah, so just to complete the implementations, we also have some implementation of VCPE where we actually use the zero-touch configuration capability, and also using multipathing over dissimilar cost links. So that's one very interesting use case where we work as a virtual network function, and DLSP is actually doing the hard work. We also use DLSP in orchestrating our cloud, so it can discover the network, and then we actually do a auto configuration of underlay network. So that's one of the main differentiating points with any existing solutions today. So many of the orchestration systems these days, they actually treat your underlay as separate from the overlay. But since we use DLSP, we can bind together the underlay and overlay and provision them together so that we can do an optimal flow configuration.
So when you're saying we, is that an Adara private cloud or Adara private cloud product or a public cloud that I can consume? What is it?
Yeah, I have this problem of saying we. So we have a cloud management system that's built on top of OpenStack, and we have like Adara has a Neutron agent implemented, and we have PCE running on top of it to do SLA-based forwarding, etc. So you can actually define SLAs for your elephant flows and ignore the micro flows, etc. It's a cloud management system that can do all this, which is integrated with OpenStack.
Really interesting stuff here. So at a really high level, some of the kind of trends at the moment are to base a lot of the decision making for paths into a controller, completely almost into a controller, and let the endpoint to be done. But I mean, I think obviously what you've identified is there are other problems to solve around, kind of a changing landscape. And you've moved the intelligence back down into a protocol where maybe then the interaction with the controller is minimalized, and you're kind of using that maybe just as a light touch point or a central point, maybe where you can get some telemetry from or something.
Yes, that's right. But when we don't have the flexibility of running DLSP on every switch, we also can take advantage of the OpenFlow semantics and run DLSP as an application on top of controller, so that we are totally unaware of what switches we are managing. But we can take more intelligent decisions if we know the capabilities of switches. very well. For example, if it's an optical switch and we know that it can do more effective L2 switching, but it can't do packet routing. So we have that context knowledge inside DLSP. And what we actually till now thought of is just DLSP can work with probing. We also have a mode of DLSP where it doesn't send the probe packets, but can utilize the link statistics and all fetched from the open flow statistics are directly from the hardware if it's running on the switch directly, and use that to kind of see the link utilization. So that we actually use in data center environments wherein the networks are very stable compared when running over a WAN.
Very interesting. So I'm going to hit you with one more awkward question, I think, and then I probably need to go on. I think we're kind of slowly running out of time here, I think. So if you put the controller, if you put DLSP on a controller, and then the controller's obviously now, is kind of visible to traffic on the network. I mean, that then suggests that you've added an attack point to the network. So then how secure is DLSP? Sorry, I can't even say this. DLSP. How secure is it? And how, are there any hardening mechanisms and nerd knobs that you can turn for this kind of, topology where the controller's actually almost not in the forwarding path, but it's got a listener on the front.
So we leverage the flow configuration on the switches so that the packets, the actual data plane packets doesn't come to the controller.
Sorry, let me rephrase. What I meant was, how do you prevent other people on the network from targeting the controller to influence, I want an attack vector. Oh, and now my easiest point of influence is the controller that's running DLSP, because I can now influence where packets go. So, have you got any kind of traditional hardening that you will do in that kind of circumstance? And how do you calm nerves of the customers when you suggest that as a route?
Yeah, got it. So sorry for my earlier.
No, it's me. It's my bad English. Just shoot me for it.
So
Sorry.
actually, one of the implementations of DLSP was in Department of Defense. So it's one of the most secure protocols that we have around. Marcelo, can you say that? Can you put in more details regarding this?
Yes. So David, what happens is every single probe, every single packet that DLSP sends on the wire is encrypted and authenticated, regardless of whether you have IPsec or not. Sometimes the peer routers, they may have just a clear text tunnel with each other, in the data center, for instance, connected to islands, where you have a secure layer 2 environment. But every single packet sent by DLSP over UDP or TCP is authenticated and encrypted. And also, the encryption algorithm, the logic for encrypting is that the key changes every couple of seconds. So you may, if you try to replicate, to do a replay attack, that's virtually impossible. If you try to mimic, to be a new peer of a router, if you collect the traffic, whatever, even if you figure out the first key, you will not get the next one. So I would say it's virtually impossible for a router to pose as, a peer when it's not supposed to be.
Yeah, and since we have our deployments in the defense, we were a defense contractor earlier, so we had some security certifications as well.
Sure. So when you would build this, then I imagine then from a provisioning point of view, if you want to go into an environment and turn the boxes on, there must be some pre-configuration work where you share certs or you share like a seeding key or something to put them in the same network?
Yes, that's correct. Yes, there is. Yes.
Okay. This is cool.
Now, if someone wants to know more about your routing protocol, is there something published that I could download and read?
Yeah, you can find more information about DLSP on the Adara's website, adaranetworks.com.
Or you can also be if you're already collaborating with any open, we have more discussions in ON Labs while discussing the PCE framework. You can follow us there. We also occasionally tweet. We attend regularly the meetups, and so you can also. We are planning to put up some blogs on our website, so you can follow there as well.
Okay, so start at adaranetworks.com and explore.
Exactly.
And how can people get in touch with you too? Do you tweet? Do you have your personal blogs?
Well, you can follow us on Twitter, Adara on Twitter.
Yeah, it's on Twitter, or you can email us to, I think it's support@adaranetworks.com.
Perfect. So thank you for being with us. And Ethan, where can people find you? I mean, most of them already know the answer, but
I am at ECBanks on Twitter. My blog is ethancbanks.com. And of course, I co-host the Packet Pushers podcast, which you can find at Packet Pushers on Twitter or at packetpushers.net.
I can't tell you how many times I've been listening to this speech in the last week or so as I was biking around. And David, where can people find you?
So they can find me on my blog at ipengineer.net. I'm also on Twitter at David John G. And I'm just generally floating around on the net, and I'm on IRC, and my old username of LSP42.
So you are making that reappear?
Trying to. I'm in talks with Twitter.
Okay.
We'll see. Yeah, they've suspended it, and it's just like, can you please unsuspend it? But I'm not quite there yet.
Okay, I hope you'll get it back. It was an awesome handle.
A big mistake. There you go.
And I'm Ivan Pepelniak, and you can find me as at iOS Hints on Twitter or on my website and blog, which is ipspace.net. And if you want to listen to more episodes of this podcast, just go to podcast.ipspace.net and you'll find everything we ever recorded there. And for more SDN goodies, go over sdn.ipspace.net, where you'll find the podcast, presentations, videos, webinars, books, everything you need to get a real-life perspective on SDN. Thank you all for being with me, and it's been a great conversation, and I hope we'll continue it in the future.